Alright, well, welcome back to the final part of respiration and the respiratory system. In this one, I'm going to look at essentially gas transport and a little bit about gas exchange. Gas transport in this case is looking at how oxygen gets from the lungs to the cells, and then how the carbon dioxide produced as a byproduct in cell respiration gets released from the cells into the blood, and how it then gets back to the lungs to be excreted in the exhaled breath. Alright, so behind us, got some basics here. This is just a diagram of blood flow. So this is the oxygenated blood side, so this is coming from the lungs. And what I could actually do on either side here is, actually I could be even more specific, I suppose, and I could separate either side. So here's our lungs, you have the capillary beds in our lungs, and this is where oxygen enters the blood and carbon dioxide leaves. So when we enter the arterial, the oxygenated side, from here to here, that's a pulmonary vein, but from here to the capillary beds, that's the arteries. But you do this in anatomy, so this is just revision. But think about the oxygenation and what levels of oxygenation there are. In oxygenated blood, the partial pressure of the oxygen of the 760 millimeters of mercury that we have in total, the partial pressure is 100 millimeters of mercury. And as that goes around and through the heart on the left hand side and gets pumped around the body into the capillary beds where the oxygen is offloaded, that 100 millimeters of mercury drops down as it comes through, and by the time we get to this side it has dropped down to 40 millimeters. So 60 millimeters of mercury pressure equivalent of oxygen has come off at the systemic capillaries feeding all of our cells. So we do get a fair bit of oxygen into our cells from the lungs through to the cellular capillaries. So that's how much we have there, and then when we get back to the lungs it's back to 40 because this is what's been drawn off to the cells. And so 40 goes back up to 100 by the oxygen coming from the alveoli into the blood capillaries. Now, that's a large amount of oxygen having to travel across the alveoli. There literally are about almost a billion molecules of oxygen in a red blood cell or something of that region. We are talking very, very large numbers. The numbers are in the PowerPoint if you want to try and work it all out, but in total oxygen in our blood system is really, there's a lot of zeros in there, which means that we need a lot of surface area to manage to get all of these molecules across as efficiently as possible, because the blood doesn't stop, it just carries on passing on by. So it's kind of like trying to get on a train while it's still moving, and in a lot of countries this is actually how it happens. Or if you happen to be a fan of the Divergent films, where the one group, the active group, has to get onto the train while it's still moving. Train slows down, sure enough, but at the same time, it's certainly more challenging to do so. So our oxygen comes in as the blood passes through and gets up to 100 millimeters of mercury pressure. So if you have a patient in your ER department and they're having trouble breathing, or they're having chest pains, etc., what you can do is take something called an arterial blood gas, which would come out here. So it's an arterial blood gas, or ABG. And that gives you a clear indicator of how much oxygen is on the arterial side feeding your cells. Now that's really important because yes, normally you can put on a little oxygen monitor, a saturated oxygen monitor, and it will tell you it's 98%, saturated in oxygen. Well, that's fantastic. But there are certain times where we don't get an accurate reading from these. So if you can't get the history, etc., then doing this will give you the actual amount because it's measuring the oxygen in the blood itself. Other things is when you're in respiratory distress, you may want to know if this person's in type 1 respiratory failure or type 2, because there's different things that you would have to do for that. And unfortunately in this particular lecture I don't have time to go into that, but maybe I'll put it into the review section at a later date, or by all means ask me questions and I can talk about that, because it's a really interesting clinical aspect of what we're learning here. Anyway, so you can take an arterial blood gas, you should be seeing the oxygen at least 80 millimeters of mercury or higher for it to be normal, and your carbon dioxide should be relatively low because it should have just been offloaded in the lungs. We take that usually from the radial artery. Here, if you're going to do that, just as a clinical point, and this hasn't really got anything to do with respiratory physiology, but at the same time a bit of knowledge can be helpful at times. If you remember your anatomy, you've only got two arteries feeding the hand. You have the radial on the thumb side, and you have the ulna on the little finger side. So if you think about it, if you're putting a needle into the radial artery, there's always a chance that you can damage it enough that it would clot off, and therefore blood would no longer be flowing down that side into feeding your hand. So then you're down to your ulna artery. So before you put a needle into anybody's radial artery, you should at least check that the ulna is patent, meaning that it's flowing. Now, you can do this relatively simple. It's a little bit of a tricky thing to show you on this film, but I'll try. So you can take their hand and you can find both the arteries here, and you can get them to make a fist. Now when you make a fist like that, if I just leave this relaxed, I'm pushing all the blood out of the palm of the hand by making the fist. You can see my knuckles should have gone white there. So when I release, you should see it all go pink again, because there's the blood flowing back in. So make the fist, go pink again. So if I block the radial artery, I should see the hand go pink again, because the ulnar is now filling up the hand. If I want to check, I'm doing it right, I can find the ulnar artery and the radial artery and try and cut them both off. Nope, didn't quite manage that one. You usually do it if you come right across here. Yep. There you go. If I release the thumb, you should see it go pink again. Well, I don't know whether the colour showed up well enough there or not, but it's certainly a test you should do to make sure that if you were to block the radial artery and the ulna wasn't patent, that person would no longer have any blood going to their hand. So that would be a very serious situation. So it's worth knowing to do that. Alright, so back to topic. Lung capillaries, systemic capillaries. In the oxygenated blood, our oxygen's up at 100, CO2 down at 40. If you took an arterial blood gas, you should have numbers relatively close to this. If your oxygen's down at 60, closer to something like that, then there's some problem here. There's not enough oxygen in the side where there should be oxygen. That would definitely give them problems with their respiration and their circulatory systems, as well as problems going on in the cells. But if the oxygen's normal, that's a good sign But again, if the oxygen's down at 60, but the carbon dioxide's now 65 or something like that, well, the carbon dioxide is way too high. So the carbon dioxide is not leaving here properly either. So simple blood gas like that can give you an awful lot of information about what's actually happening within the lungs and the circulatory system of the cardiovascular. Okay, so we're interested in how oxygen gets in and moves to the systemic capillaries. Well, 90% of oxygen is bound to hemoglobin. Now, hemoglobin is a quaternary protein found in red blood cells. So there are millions of hemoglobin molecules inside a one red blood cell, and of them there are 4 heme groups, and in the middle of each of those 4 heme groups there is an iron molecule. Iron molecule, I'm saying. There is iron, it's not a molecule. It's an iron. An iron. That's a good one. So the hemoglobin has 4 iron in it, and each one of them will bind an oxygen. So 90% of the oxygen will be bound to the hemoglobin inside the red blood cells. 10% of it will travel just dissolved in the blood plasma, but the bulk of it will be bound to the hemoglobin. So if we get low on hemoglobin or red blood cells, we get low on oxygen, and that's what we call anemia. And anemia is characterized by tiredness because, hey, you don't have oxygen, you can't produce energy efficiently. So your cells are tired, you're tired. So very good, simple understanding of that. So 90% bound there, attaches on here and is released here. But what really makes it release at the capillary beds? Well, there's a number of mechanisms, but the one that we look at the 200 level is the effect of acidity and temperature. So as acidity and temperature increase, the offloading of oxygen also increases. So as it becomes more acid in the capillary beds here, oxygen comes off faster from the red blood cells out of it and into the cells more quickly. Now that's great because remember, if you're exercising and you need more oxygen because you want to make more energy, well, the local area will be becoming acidic because you're producing a certain amount of acid because of the carbon dioxide increase and the movement of that moving back toward the lungs, and that naturally pulls off more oxygen to allow you to make more energy to make up for that. So it's a very nice little system. Temperature is another one. To make energy, to make ATP, is about 40% efficient. 60% of the energy that started with the glucose molecule and ends up in the ATP, 60% doesn't end up as ATP, it ends up as heat. So that's the other thing you notice when you exercise is you warm up quickly, and that's because you're producing a lot of heat as a byproduct. So both of these things actually increase oxygen offloading at the cells, which means that you can be more efficient and actually make the energy and do the things that you need to keep going. So whilst in the PowerPoint there's a lot more information on that, that is what I want you to take home for in terms of oxygen transport in the blood. So that leaves us one other thing to cover, and that's what happens on the deoxygenated side. And we've talked a little bit about this already. We know that carbon dioxide is picked up, we know it's a byproduct, we know that in water and blood plasma it's going to become hydrogen ions and bicarbonate, and that could become a problem because of the hydrogen ions. So how is it travelling in the blood? Well, 10%, like oxygen, is dissolved in the plasma. 20% of it is actually bound to the hemoglobin as carbamino hemoglobin. So that's 30% taken care of, so we're good. So what happens with the last 70%? Well, that travels as hydrogen ions, so that 70% goes through this process here. Now, that's not all terrible, because in the blood, if we just draw a quick blood vessel, and we put a red blood cell in there, put one over here, so these are red blood cells. And in this case it would be a vein. Alright, so we've got our carbon dioxide. I'll do that in green, try and make some other colours. So our carbon dioxide is coming from the cells, so we'll do our cells here. CO2 is released, it's coming through there. It's going to interact, so CO2 is going to go through this point here, interact with water, CO2 plus H2O, and through the end of that we're going to end up with hydrogen ions and bicarbonate ions. Now, they kind of balance each other out, so what's the problem? Why do we care? It's because hydrogen ions are being produced in the cells by other activities, other chemistry that it's doing, and other acids are being produced as well, so positive charges. So we don't want any more positive charge in here than necessary. Because remember, we're trying to hold the pH here between 7.35 and 7.45. So any big buildup of this coming from respiration is potentially going to cause a bigger problem. So what happens with the hydrogens? Well, at the cells, capillary beds, the hydrogens that are formed in this actually, the CO2, redraw this slightly and more accurately, is that the CO2 comes in and goes all the way into the red blood cell. Now, when it's in the red blood cell, it goes through that process, and so you end up with hydrogen ions inside the red blood cells. So they're not in the blood fluid, so they're not making anything acid. So that's really good. And with the bicarbonate that's produced, it's sent out into the blood as a negative charge to help act as a buffer to any other of the positive ions building up. So 70% of our carbon dioxide travels inside the red blood cells as hydrogen ions because of that equation, because it's converted. The bicarbonate leaves, enters the blood and helps to act as a buffer. Now, maintaining that pH there, the first defense mechanism is bicarbonate buffer. There's a phosphate buffer involved in this as well, but we don't look at this at this stage. So the first defense is this bicarbonate buffer for the blood. The second defense is what we looked at in extrinsic control, is breathing faster, blowing carbon dioxide off. Because remember, if we breathe faster, we're drawing off more carbon dioxide because this reverses, and therefore there's less acid in the blood. So that's two defenses. We've got bicarbonate in the blood all the time, and then we can blow off carbon dioxide faster by breathing more quickly. The final one is in the kidneys, and we'll look at that when we look at the urinary system. So here we are at the vessels, at the capillary beds. We've got hydrogen inside, bicarbonate outside. Now, because we've built up quite a bit of hydrogen ion inside the red blood cells, we see a shift occur. Chlorine, which is in the fluid, in one of the electrolytes in the fluid, is attracted by the positive ion, so it actually enters the red blood cell as well. So this is referred to as, where am I going to put this, but here, the chlorine shift. It's moving at the cells capillaries, it's moving into the red blood cell. So we're seeing a drop down in chlorine in the blood, in the plasma phase of the blood. Now, 70% of that goes through, pumped by the right side of the heart up to the lungs, and as it gets to the lungs here, this equation is reversed, and so we get CO2 back, so the CO2 can leave and enter the lung spaces in the alveoli. So the reverse of this happens, and so what we see is the hydrogen ions reforming with bicarbonate. Bicarbonate goes back in, merges with the hydrogen ions, reforms carbonic acid, and that breaks down to water and carbon dioxide. Carbon dioxide comes out and enters the lungs. The positive charge is left here now. So the chloride ions come back out. And so we see the chloride shift opposite in the reverse direction, coming back into the blood. So the chloride levels of the blood increase a little bit. Alright, so this is how I transport oxygen, so I said here, and transport of carbon dioxide here. I'm talking about chloride shift there. And again, the equation. We've also been able to talk about the first two buffering methods of maintaining the pH of the blood, or acid-base balance in the blood. And that is by the bicarbonate levels in the plasma, and also the ability to respond to increased carbon dioxide in the blood to increase ventilation, i.e. breathe faster to blow off the carbon dioxide and drop your levels in the blood. So that's respiration. Thank you very much for listening, and of course email me with any questions that you have.